Hello everyone, welcome to my talk. Today I would like to share my recent work entitled Quantum Correlation Alignment for Unsupervised Domain Adaptation. This work has been published on Physics Review A. Transfer learning is a crucial subfield of machine learning. Transfer learning aims to accomplish tasks on an unprocessed datastate with the known information of a different but related datastate. In the realm of transfer learning, domain adaptation specifically attempts to predict the levels of the unprocessed datastate based on the given labeled datastate. Domain adaptation has been widely used in natural language processing, computer vision, and reinforcement learning. Given a labeled source domain, DS, and an unlabelled target domain, DT, generated from different data distributions, the goal of transfer learning is to predict the levels of DT with the knowledge of DS. And this figure shows the difference between the learning process of traditional machine learning and transfer learning. In terms of the levels of the given data, transfer learning can be categorized into semi-supervised transfer learning and the unsupervised transfer learning. The semi-supervised transfer learning refers to a common method where the unprocessed datastate has a few levels. The unsupervised transfer learning focuses on the task where the unprocessed datastate is totally unlabelled. In terms of the methods, transfer learning can be categorized into instance-based transfer learning, feature-based transfer learning, relation-based transfer learning, and model-based transfer learning. According to the characteristics of the feature, transfer learning can be categorized into homogeneous transfer learning and heterogeneous transfer learning. The correlation alignment algorithm is one of the most representative transfer learning algorithms. The QCORAL firstly decorrelates the labeled source domain data to eliminate its unique data characteristics. Subsequently, it aligns the decorrelated labeled source domain data to the unlabelled target domain data to reduce the domain shift. The goal of the QCORAL is to minimize the discrepancy between the source and target domain datasets by aligning their second-order statistics, namely the covariance matrix. The QCORAL directly aligns the datasets without projecting the data to their corresponding subspecies, resulting in a much more concise procedure than other domain adaptation methods. After the data decorrelation and alignment, a classifier will be trained on the aligned labeled source domain datasete and applied to the unlabelled target domain datasete to predict the target domain levels. With the QCORAL, the levels of an unprocessed target domain can be obtained efficiently without the need for the costly manual labeling. And this is the covariance matrix of the source domain data and the target domain data. According to the goal of the QCORAL, the objective function can be defined as this equation. Subsequently, we can obtain the optimal transformation matrix A star. Thus, the decorrelated source domain data and the aligned source domain data can be obtained. However, the algorithmic complexity of the QCORAL can be prohibited with the increase of the number and the dimension of the given data. In our work, two different types of quantum implementations of the QCORAL are presented. One implementation, namely the quantum correlation alignment algorithm, namely the QCORAL, can be performed on a universal quantum computer, achieving exponential speedup in the number and the dimension of the given data. First of all, we encode the source and the target domain data into the quantum state psi-xs and psi-xt. In addition, the quantum states corresponding to the source and target domain covariance matrix are ρcs and ρct. Then, the singular value decomposition of xs and xt are like this. For simplicity of the subsequent computation, we extend the matrix xs and xt to xs tilde and xt tilde. The QCORAL is achieved by invoking quantum phase estimation, quantum Fourier transform, the HHL algorithm, and quantum singular value decomposition algorithm. The concrete steps are as follows. Compared with the classical correlation alignment algorithm required algorithmic complexity in time polynomial to the number and the dimension of the given data, the QCORAL can achieve exponential speedup. Although the QCORAL can be performed on a universal quantum computer with exponential speedup, the implementation critically requires a high-depth quantum circuit and fully coherent evolution. Alternatively, the CORAL can be implemented on the near-term NISQ quantum devices with a variational hybrid quantum classical procedure. The VQCORAL combines the quantum computation and the classical optimization together to implement the algorithm with parameterized quantum circuits. Compared with the QCORAL, the VQCORAL can achieve the procedure of correlation alignment with shallow quantum circuits. Specifically, the number of parameters utilized in the VQCORAL to achieve the procedure of correlation alignment is polynomial to the number of input quantum states. However, the cost of the classical CORAL will be exponential in the size of qubits when the original data are given in the form of quantum states. Subsequently, we will present the implementation of the VQCORAL and explore two different specific configurations in detail. In configuration 1, inspired by the idea of classical neural network, we designed end-to-end VQCORAL. The corresponding cost function can be defined as LV, and with U theta representing an L-depth parameterized quantum circuit. In configuration 2, we accomplish the procedure of correlation alignment in two successive variational steps. Concretely, the square root of the source and target domain matrix can be computed by the iterative process. Then, we define the cost function LM1 and LM2 to accomplish the procedure of matrix multiplication. To demonstrate the feasibility and the efficiency of the VQCORAL, three numerical experiments are presented. The no adaptation model, namely the NA model, the classical CORAL, the VQCORAL, are applied to the synthetic datasets. The synthetic iris datasets and the handwritten digit datasets, respectively, to evaluate their performance. According to the simulation results, the VQCORAL can achieve comparable or even better performance than the classical CORAL. The NA model is set as the baseline model. In addition, the classical CORAL is also selected as a performance comparison to the VQCORAL. As to the VQCORAL, we design parameterized quantum circuits with hierarchical structures as presented in this figure. The classical optimization algorithm, the decorrelate, is selected to optimize the cost function. To evaluate the performance of the VQCORAL, we present three different numerical experiments. For the two synthetic datasets generated from different distributions, the VQCORAL outperforms the classical CORAL and the NA model with a 2-qubit at-layer variational quantum circuit. For the synthetic iris datasets, the VQCORAL also shows outstanding performance with a 2-qubit at-layer parameterized quantum circuit compared to the other two models. For the handwritten digit datasets, namely the MNIST and USPS datasets, the domain adaptation procedure can be implemented with by an 8-qubit 16-layer parameterized quantum circuit to achieve comparable performance to the classical CORAL and better than the baseline model. Although we propose two quantum versions of the CORAL, however, some open questions need further study. First of all, the QCORAL requires a high-depth quantum circuit and fully coherent evolution, which are actually prohibited in experiments at present. In addition, although the VQCORAL algorithm can be realized with limited quantum resources, the performance of the variational quantum algorithm actually depends largely on the specific design of the parameterized circuits. Hence, it is well worth exploring how to design quantum circuits specifically to achieve optimal transformation. Although some further exploration is required, it is demonstrated that quantum techniques can make a contribution to the field of domain adaptation. Thanks for listening.